right, it's 12:30, so let me give you some reminders for the rest of the semester. The presentations for the class, which means the report, the 6 pages report, the PowerPoint slides, your OLA presentation are going to be the last 3 lectures in April. Okay? Because there's, from past experience, there's no way we can find another room in May, so they're going to be during the last weeks, which means plan ahead, right? Don't show up and say, can I be the last? Because you're being called and you will be the first. Okay? And it doesn't go first come, first serve on this case. Last come, first serve. That's the new policy. Which means if I don't hear from you, you're first. Okay? That's one thing. The second thing is we were planning to give you 6 homeworks, and seeing the very slow process of even preparing the solutions of the homeworks, I asked Suvik to give you 6 homework, but also to give you the solutions so you can study them, but we will not have to submit a 6 homework. Okay? I'm not doing this to reward anybody. I realize things are not going as the way I envisioned, so I think that's the best option for everybody. All right, so what else? Anything else I forgot? All right, so what I'm going to do is, because we went over literally 8 minutes to cover variational inference for linear regression, I'm going to go back today and spend maybe 15 minutes on the topic, okay? And in some sense, if you know nothing about linear regression, seeing this in the context of variational algorithms is good, because the results they look very close to the exact inference that you can do for this type of problem. All right, and then once we finish with this, we will discuss about the Gaussian mixture problem, which is mathematically way more intensive, but also way more useful. And then maybe we'll generalize this to sort of any distributions from the exponential family. And next Tuesday, we will start talking about approximate methods, inference methods in graphs, in particular the expectation propagation, which is sort of one of the standard methods for doing inference in very complex systems. Things will get progressively more complex, okay? And you may say, but this is statistics, is not machine learning. No, it is machine learning, it's not statistics. Statisticians don't know much about this. Machine learning people need to know more, okay? So I'm saying this to avoid any comments on that subject. All right, so let me put all the equations for Bayesian regression. So we basically were given x, y data, if you like, pairs of data. The y here is denoted with t. So I'm using, I think, the notation. This must be from Bishop, I'm guessing. So the linear regression comes, we write a response t at any x as w transpose phi, where phi is a vector of basis functions. You can think of this being in one dimension, for example, 1x, x squared, can be splines, can be radial basis functions, can be anything, okay? And we also had some noise, and if you write this in a probabilistic form, the likelihood for IID data looks like that, okay? So now, to make the analysis simple here, I'm going to take the precision in this model is known, and I think I have 2 or 3 slides in the notes where basically we can remove that constraint, and it doesn't add really any much difficulty to the problem. So in Bayesian regression, right, the idea is we're going to take everything to be random. So W is going to come with some prior distribution, and the prior depends on this precision alpha. And for now, we're going to assume another hyper prior basically for alpha that is a gamma distribution. You should know by now that gamma distribution comes always as a prior for precisions, everywhere in machine learning, okay? And I think we also discussed that you can generalize this where you make this alphas not to be alpha minus 1i, but you can put a different alpha in the diagonal of the covariance, and that's how you get this relevance determination methods. You can figure out which of the W's are needed to do the proper regression. But right now, this is what we have, okay? We mentioned that there is an analytical solution to this problem. You don't supposed to know it, so if you know nothing about regression, we will try to do this from scratch in the context of variational inference. So to do variational inference, we need the joint likelihood, and here is my observations. W and alpha are the unknown parameters. So the joint likelihood is written P given W, right? P doesn't depend on anything but W. There is a beta there, but I'm taking beta to be constant. P of W given alpha and P of alpha, okay? And basically this is, since we talk about probabilistic graphical models, basically I would have thrown a picture like this. This defines all the equations we have seen up to now, okay? All right, so we're going to assume, we want to calculate the posterior of all the parameters, and all the parameters here are W and alpha. So we want to approximate the posterior of W and alpha given T, and since we do variational inference, we approximate like that. Okay? It doesn't mean that this is right. No, it's not right. It's an approximation. That's what variational approximations are about. They are approximate methods. All right, so we factorize this posterior to look like this. All right, I asked you last time, I'm not going to ask you this time so I don't get another headache. So the log of each of these distributions in the factorization, so for example the log of T of alpha is basically the expectation of the joint log likelihood with respect to all the other parameters. And in this case, since I'm calculating Q of alpha, the other parameters is W. Okay? So what you need to do in the algebra, you need to expand the joint log likelihood, keep only the terms that depend on alpha, and in those terms, anything that has W, you have to take an expectation with respect to W. So if you plug in P of alpha, it's a gamma distribution, that's the log. This is a Gaussian, easy to calculate, so you need expectation of W transpose W. I don't see the expectation of W here, right? If you take a Gaussian and you take the logs, you're supposed to get an expectation of W also. Why is not there? I mean, I just visually realize I don't see an expectation of W there, right? Why is that? Because, yes, why I don't see an expectation of W? Thank you. All right? I mean, if I see something right and in my eyes looks wrong, I have to think myself. So it's good that you think that too and you say, wrong, mistake. All right? But it's obviously not a mistake. Okay. So that now we need, when remember the constant terms are terms that depend, for example, maybe just on W, or they're constant terms really, and we don't care because this is a distribution on alpha. The only reason we keep this is because it multiplies alpha. So you can immediately see, you can combine this log term and that term, you can combine this constant term and this term times alpha, and basically what you get is the log of a new gamma distribution with updated parameters. So the posterior looks like this, and effectively you can see that one of the reasons someone is using a gamma distribution for alpha is really because even the approximate variational distribution for alpha is a conjugate. It comes basically to be an update of the coefficients of the prior we had for alpha, right? Before we only had this alpha 0 B0, now you added this nice thing, so it's very nice. Okay, even though it's an approximation. All right, you do the same thing for W, so you expand the joint log likelihood. The algebra is basically straightforward, but I wrote it here, rather than having these summations, I wrote this in the matrix vector forms, introducing the design matrix tree that involves all the basis functions calculated at each of the given data points, right? That's the design metrics. And T is the values of the function that we have given at the given input points. So this is a Gaussian. You can see square, you can see linear term in W. So if you complete the square again, you get a Gaussian similar to the prior we started, but with updated parameters. And I emphasized, since maybe you haven't seen this even in the context of simple Bayesian analysis or even any sort of MLE or calculation will give you an alpha there. Here we get the expectation of alpha. Okay. There is no expectation of beta because here I'm taking beta, as I mentioned, to be constant. All right. So something to emphasize: if you look, for example, in the variation approximation for W, you notice here to be able to compute this, you need to know the expectation of alpha. And to know the expectation of alpha, all right, you need to know the expectation of W transpose W. So this is an iterative process. And actually in some books, because this sort of mimics the expectation maximization process, right? You say do this, update that, and plug in, etc. So in a lot of books, you will see the presentation on this as here is the E step, here is the M step, but it's really slightly different, okay? But I notice lots of machine learning books, they give these algorithms as if they were EM algorithms. All right, you can calculate the posterior. This is a very important step, right, that when you do variation approximations. So the exact posterior, so if you want, I'm sorry, this is the predictive distribution, right? The predictive posterior distribution. So once you train the system, you say now, at the given X, I want to know what the response is. I'm taking the response here to be scalar, and this bold T is the data, right? So that's the predictive posterior. So that's basically the likelihood. What will you get if you know W times the posterior, where all the parameters are integrated out? And the key ingredient here is you are not going to plug in the actual posterior. You will actually plug in the variational approximation, which is Q of W. Okay? Now, of course, the exact posterior is very easygoing Gaussian. So we could have done this, but here we demonstrate this as an example. So you plug in Q of W, and this is the marginalization. You remember you have something. This Gaussian has a mean that's a linear function of W, and then you have times the W and integration of W, right? So this is really a marginal distribution on T, and if you look at the formulas for linear Gaussian systems, I told you to have them posted in your desk, all right? Look at them every day, because these equations, you use them every day, 10 times. So you don't have to search, okay? You look at them, you plug them in, and basically you get another Gaussian, and you can see the variance. It's, of course, dependent on X, so it varies with X. And if you plug in things, okay, you will notice again that this matrix Sn depends on the expectation of alpha and the design matrix phi. Okay, so obviously the expectation of alpha, we know it, assuming we have computed the variational approximation for of the posterior of alpha. Okay. The final thing that I'm going to remind you very quickly is every time you do variational inference, variational approximations, you always have to verify that your calculations are correct. And the only way you can do this is by calculating the lower bound and showing that the lower bound increases basically monotonically. If something happens and doesn't increase monotonically, there is a problem. Okay? So I remind you the lower bound is the expectation with respect to the variational distribution Q of the log of the joint likelihood divided by the variational distribution So it's written like that. If you expand all the terms, you know everything. So it's really algebra, right? You just plug in things, but you know what? If I ask you to plug in and give me this in half an hour, I bet most probably none of you will complete it. Okay, you agree with me? All right, absolutely, okay? And the reason none of you will complete it because you hesitate to actually do the algebra ever. So you look at it and you say, yeah, easy. No, it's not easy, because if you try to do it on your own for another problem, you will mess it up. Okay, so there is an educational purpose of doing this for simple problems like a regression problem, because you do all this algebra, you plug in and plug in and plug in, and then you know what? By the miracle of net truth, what is the final answer? Do I have a final answer somewhere? Did I delete the slide with all of you? Because the final answer comes to be very nice. Somebody ate my slide, okay? So anyways, we have all the results here, right? But when you add them up, you get a very nice answer, okay? End of story, okay? And this is a very good use of this lower bound in model selection. So for example, if you're doing regression and you have a bunch of data and you say, let's say you use polynomials in this case, you say, what's the order of polynomials that I need to use to better represent the data? If you try to do maximum likelihood say, keep using higher and higher and higher order of polynomials, because the likelihood will keep increasing, but you will overfit, okay? So with Bayesian inference and using this lower bound, that's not the case. And you can see here, it says m equals 3 is what explains the data, okay? And I think we already discussed, and I may come back today also, if you do model selection, right, and you put, let's say, some uniform prior over the space of the order of polynomials, in essence, this is, this calculation effectively gives you an approximation to the posterior of the models, right? So basically, this is nothing else but the posterior of the model with polynomials m equal to 3. Okay? So this is a very nice way to do model selection. Right, and this is a very nice picture from, not picture, it's just really a little algorithm run. These calculations run in MATLAB using the Kevin Murphy's toolbox. So basically, on the first row, it shows you the method in action, so a calculation of the posterior of these models of different orders of polynomials, given some data, which here you have 5 data points. And you can see that if you have very few data, the method basically, the variational inference tells you, you know what, use the lower order polynomial, okay? The lowest model is what you need, but when you increase the number of data, for example here, it immediately puts a posterior on m equal to 3 very low, and it tells you not select a model with m equal to 2. This method is empirical Bayes method, basically, okay? This is what, for those who took the course in the fall, or they are reading machine learning books, this is basically the evidence approximation. It doesn't do as well. So you can see, for example, in the evidence approximation here, it puts a lot on this posterior for m equal to 1, but here basically it's almost equally distributed when you have a few data, because in that case is the prior that dominates the this posterior. Here there's no really such a thing, so this is not fully Bayesian, but this is fully Bayesian. All right. I am not going to do this, but I mentioned that you can extend this type of calculations when you take this precision in the likelihood model also to be a random variable, right? So you can put a prior on that, and you can basically repeat all the calculations, and you can calculate. So if you put a gamma prior on beta, you can calculate an approximate posterior that is also a gamma, and you can see the formulas come very nicely in a very close form, and the algebra is really nothing significant, and you can actually calculate the predictive distribution, and it's not surprising actually. For example, you look at the variance, comes to be identical with the previous result, but instead of beta, you have expectation of beta. Okay, so lots of the answers really sort of are expected. Okay, all right. Okay, so what I'm going to do is I'm going to switch now lecture, and I'm going to come back. Remind me, slide 16 after we move from this. And do a very fundamental problem. Okay, so we're going to discuss something that looks trivial to lots of you, but you will, if you search the literature, you will find lots of papers written because it's an extremely fundamental problem that comes everywhere. So the idea here is we're talking about a mixture of Gaussians, and we're interested to do approximate Bayesian inference for a mixture of Gaussians. So what does that mean? You know data come from a mixture of, let's say, 3, 4, 5 Gaussians. I'm giving them to you. I don't tell you what Gaussian generates the data. And I'm telling you, go and calculate the posterior of the mixing components, and for each component, compute the mean and the variance. Right? That's not a trivial problem. Okay? Now, there's lots of different simple ways to do, and so I'm going to pretend that you have never seen this problem before. In other words, you don't know all the solutions. Okay, so we're going to concentrate on variational inference only. Okay? And again, this is very fundamental in machine learning. It comes everywhere. And actually, this concept of Gaussians, you can even put another word and make it a mixture of Gaussian processes. Okay, we will not discuss that in this course. And actually, to make it even more relevant to research, instead of mixture, you can say infinite mixture of Gaussian processes. So basically, you can do sort of relevance determination and throw infinite number of components and let this analysis figure out which ones are needed. Okay, and it doesn't have to be Gaussians; can be Gaussian processes. And this needs to lots of very recent sort of relevant research, basically, that some of you or someone here or there may be interested to research. Okay, so let me discuss the problem. No need to read anything. So remember that we have observations of some data xn. Each data has a latent variable affiliated with it that I call it Gn. So you can think of Gn being a labeled variable. Right, tells you it is this component of this Gaussian or that Gaussian or that Gaussian. So that's the latent variable. It's of the let's say if you have a mixture of two Gaussians, each Gaussian will have its own mean and variance. All right, and this latent variables will be defined through some prior model, and the parameters of the prior model are called here pi. And I will give you the specifics on the slides to come. So the joint likelihood, so this is the observations, these are the latent variables, these are the various parameters to define the priors. So basically, you can see this factorization also graphically. The joint of likelihood would be the probability of x given z and lambda and mu, the probability of z given pi, the probability of mu given lambda, and the probability of lambda. So this is sort of a very heavy, very simple graph, but the calculation, you will see it's not, it's painful, okay? But it is a calculation that, again, if you do it once, you will get a sense of what it is and how it works, okay? So I remind you, for example, in the mixture of Gaussians, right, if you put this joint likelihood together, this comes to be a Gaussian. But if I condition x on z, you don't get a Gaussian. Okay? I mean, if, you know, so I'm sorry, not if I condition x on z, if I integrate on z, okay, you don't get a Gaussian, right? But the joint likelihood is a Gaussian, and that's why we operate with it. Okay? So I want you to look at this distribution and tell me that you understand it. So P of x given z looks like that. Can you tell me everything? Is that okay? I mean, I'm going to need to compute, right, this every term. So P of x given z and the other parameters is given like that. So I have n data points. I have a mixture of k components. So does this make sense? So z and k takes what values? What are the values z and k takes? 0 and 1. So for every data point, right, only one of these terms in that product is going to be a Gaussian, and that would be only for the k equals z and k equal to 1. Right? We have seen this about 1,000 times up to now, and it is sort of a very compact way for writing things. Everybody's in? Okay? You know, those who listen to this tape from home because they have nothing else to do, right, you should maybe scream once or say something so they think that I'm not talking to a wall. Right? It's helpful. Because, you know, lots of professors like talking to themselves. All right? So, okay? I can even pass you the microphone. All right. So we agree on that. So I am going to, so I'm going to put a prior on z, and remember, so, you know, we are talking about a mixture model, so I'm going to define this mixing coefficients pi, and I want you to look at this and tell me what's pi k then? I mean, the way we have it here. Remember, for every point xn, there is a zn. So what is this here? The prior that I am using is, so over all the data points, right? What is this? What is this conditional distribution of z given pi? So if you look on, let's say at a given point n, only one of those things, for one of the k's, this will be equal to 1, and this will give you pi k. All right? All right? And I'm going to put a prior on pi, and that prior is going to be a Dirichlet prior. Okay? And that's why I mentioned that these ideas can be easily extended to infinite mixture of Gaussians by substituting here, by using a Dirichlet process basically to do that. So here we use a Dirichlet prior, so this is the parameters alpha 0. I want you to remember all the notation, okay? And you may say, why a Dirichlet prior? Because basically it's going to make all the posteriors to be nothing else but updates basically the parameters of the distributions that you see right now. So basically these are conjugate priors, okay? So they are going to make the algebra easy, okay? And now we need to put a prior on the parameters mu and lambda, and you may have seen this for a multivariate Gaussian. You may not have seen it. So basically we write this as a product of all the components of a Gaussian, all right, with lots of unknown parameters, but you know, here the precision depends, the precision, this condition of the precision, and then with the precision we put a wizard distribution. This is, you know, in one dimension, you know how this would look like? This will be invariant Gaussian, and what will that be? For the precision, what did we say we use as a prior? We actually did it on the regression problem. What was the prior on the precision? It was a gamma. So the wizard distribution basically is a generalization to multivariate variables of the gamma distribution, right? I mean, really, if you think, the wizard distribution is sort of a distribution over symmetric positive definite matrices. Okay? Very nice distribution. I mean, if you think distribution over matrices, yes. And what of those symmetric positive matrices here is that variance lambda k. Okay? So this is, again, it is standard. All right? So when you have both mean and precision unknown, okay, you write like that. If actually you do not use the precision but you use the variance, basically you can write the same thing, but instead of a wizard distribution, you will put an inverse wizard distribution. Okay? So really what you use, the algebra you can manipulate in one way or another, but using here precision makes the algebra way easier. So there is a lot of unknowns to start with, and lots of hyperparameters, right? So you can plug in some reasonable values, and I indicate some of those here. So so we need to approximate now the posterior of all of these massive unknowns, and those unknowns are the posteriors of the latent variable z, the posterior of the mixed coefficients pi, the posteriors of the means mu, and remember mu is a vector, but of every component, so I have a lot of those, all right? And the posterior of this variance is lambda, and I have a lot of those, okay? So this is sort of written in a compact way, and for now, the only sort of, what I'm going to do is, I'm not going to write this as q of z, q of pi, q of m, q of lambda, because if we, I mean, as a minimum, right, if you expect to get a conjugate, if you expect to get a posterior that has the form of the priors, obviously you're going to get, let's say, looking at mu lambda, you're going to get some factorization of mu given lambda times a variation distribution of lambda. So you want to keep them like that together, otherwise you're not going to take advantage of these conjugate priors that you use, okay? So this is a little bit different from the factorization that we did before. Of course, we don't know what is going to come, how this is going to factorize, and it will be interesting to see. So basically, you can think here, we factorize the joint posterior, right? But we factorize it in a way that in one of the factors, we have a group of variables. And there's a whole area, actually, in variation methods where you do this for a purpose, okay? You are going to update a group of variables together rather than separate. Okay, so we start with QZ, and the algebra is going to be painful, so I'm going to try to keep clicking, assuming you give me a sign that you understand nothing, and in that case I will click twice. So the log of Q of Z, right, that's the optimal distribution, is the expectation with respect to all the other variables, pi, mu, lambda, of the log of the joint log likelihood, right? Okay. So what I'm going to do is we're going to expand this, right, and keep only the terms that depend on Z, right? And let's see what type of distribution it comes out. So the only terms that depend on Z is from this condition of Z given the mixing coefficients and this likelihood term, okay? This depends only on pi, so this expectation is with respect to pi. This depends on mu and lambda, so the expectation is with respect to mu and lambda. Algebra never helps, okay? And the reason I used to insist that you guys type these things in your homework, when you type, the answers are obvious. If you do this by hands, you will never be able actually to make this to work. You will have a complete mess. So if you take P of Z of given pi given like this, you take the likelihood given like that. These are the previous formulas. So you remember we're taking logs here, so it will be Z times log of pi, and then will be an expectation with respect to pi, and here you're going to have Z times log of this, which is a Gaussian. So obviously you're going to get z of log of something, and that something is what you see here. All right? This term comes from here, and all of these terms come from where? From this Gaussian. Can you see it? Yes? All right. Okay? So this comes basically from the normalization factor. We don't really care about the constant term. And okay? And they are painful terms because now this log of rho depends on the expectation of log of pi k, all right? Obviously, you remember we're going to have to do iterations, so to be able to compute this term means we have to find the variation approximation for pi. To complete this term, you need to find the variation approximation for lambda. To find this, you need to know the variation approximation for mu and lambda, the joint basically, okay? So we're not yet there. So this is the result, okay, where this rho depends on these other posteriors, but obviously you can immediately see that this variation approximation for the posterior of z, it's basically written as rho to a power z. Okay? You remember what we had in the prior here before when we started? Instead of rho, what did we have when we started? What was there before? It was pi, the mixing coefficients, okay? There we had pi, all right? So if you normalize this rho, all right, so you can write this with an equal sign, you get basically rho divided by the summation of rho's over j for every data point n. So distribution looks like that, which is identical to the prior that we started. So this can you give a physical meaning? What's the buzzword that goes with R now? So before we had the mixing coefficients to start with, right? Now we have observed the data and we have updated the posterior of Z. So what's the word that goes with R? The posterior responsibilities. Okay? So basically R tells me what's the responsibility the component K takes to explain point N. Okay? And when you actually are going to plot this, the way you plot this responsibility, every point you assign many colors, all right, corresponding to the different Gaussians, for example, and you can put a little bit of red, a little bit of blue, a little bit of yellow, depending on these posterior responsibilities. And actually, when you do these graphs, they look wonderful, and in the literature, that's how people demonstrate the posterior responsibility. Now, if you're color blind, good luck, okay, but these are the posterior responsibilities. Okay, and we already have discussed this when we were talking about expectation maximization. We spent lectures and lectures on this because this is a binary variable. Basically, the expectation of z and k is r and k. You remember that? Because z can only take values 0 and 1, right? So the expectation is equal to the probability, and that's the posterior probability, which is r and k. Now, the only problem up to now is, right, that we have a nice form for this, but this form for this R or rho depends on many expectations with respect to the order distributions. So unless we can actually complete all of this, we are going nowhere. I mean, it's nice to say that this is what it is, but how do you compute rho? And so we will keep going and see how that may come. All right, so I'm introducing definitions that I think we have seen them when we discussed about expectation maximization. So this is the effective number of points in the Gaussian K, all right? So basically you go through all the points and you sum these posterior responsibilities. Now this is the effective sample mean on the Gaussian K, all right? So you take all the x's, you multiply them with the posterior responsibilities, and this is the effective variance. Okay? So basically I'm defining this because if you have these definitions, you will see that the algebra is going to simplify. And one identity that you may want to pay attention, because it comes handy not just on this setting but in many related settings where you have these responsibilities. It is a very nice identity that comes directly basically by taking the definition of SK and expanding it. Okay? So somewhere in the derivations, we will not see it today, but when you read the notes, this is a calculation that comes here. Okay. So we want to calculate Q of pi, mu, and lambda. So this will be the log of that, of the Q of pi, mu, and lambda, will be the expectation with respect to z of the log of the joint log likelihood. The only terms we're going to be keeping is anything that depends on p, mu, and lambda, and in those terms, anything that contains z will take expectations. So basically what you get is, you get from the prior, you get log of the prior of pi. From the prior, you remember we had a joint distribution of mu and lambda, but Gaussian wizard distribution. There is a z that depends on pi, so we're going to have an expectation of that. And this z here, inside that term, you remember we had a Gaussian to the power z, so the z will come down, so we'll have an expectation times the log of the Gaussian plus constants, okay? And interestingly enough, right, when you look at this distribution, okay, my thing just died, okay? All right, so when you look on the distribution, does anybody have batteries with you? That's a very stupid question, right? It's like asking me, do you have any fire for smoking, right? Something like that. Okay, so you have no batteries. How can you leave home without batteries? That's unacceptable. Okay, so you can see from the equation there, right, that the variation posterior for pi, mu, and lambda certainly factorize over k, right? Because you can see the two summations on k, and we have log. So when you get rid of the log, basically you get the factorization over k. So that's very nice, okay? So, so what I'm going to do is I'm going to plug in the prior. So we have the prior of pi, it's there. The condition of z given pi. We know the expectations of the z's are the posterior responsibilities. So we plug in all of this together, all right? Actually, sometimes batteries have life if you have another, but I need also to move the okay, this the button. Oh, I need to change. Okay, all right. Okay, all right. So let me try. Let me try. Okay. Have to learn the new thing here. All right. All right. So this goes up. Okay. This goes. Oh, I see. Okay. All right. So, oh, this is heavy lighting. Nice. This is extra powerful. It comes from Beijing. You know, when planes fly, you go up on the skies, right? Don't use it outside the classroom, okay? All right. It's very powerful. I will confiscate it after that. So, basically we need to substitute, right, this here. This is what we get. We need to substitute this in there, all right? Substitute the expectations, and let's see, okay. Let's see what we get, okay? So from these calculations, basically, again, I don't want to give you all the algebra, but there are some tricky things that come all the time. So if I notice them, I need to tell you what's going on. So basically, we substitute in this expectation with respect to Z of the joint log likelihood, okay? I am going to use also the idea that the prior for mu and lambda, it was factorized as over K as Gaussians with some precision that then comes with some wizard. So you're going to have to take logs of this, and you may say log of a wizard distribution of a distribution over positive definite matrices. Well, yeah, you have to do it because it builds character, right? You have to do this. So you take this logs, etc., and at the end of the day, you get basically, you look at the terms that involve only mu and lambda, and you look at the optimal distribution. So out of this, you can extract only mu and lambda, and you can see log of Q star of mu and lambda is basically these two lines here, right, that involve lots of interesting things. You know, it is not surprising. You need to use the responsibilities there, okay? And, all right, so this is the distribution. Now, does this distribution, so from this distribution, can we say anything what type of distribution it is? It's very difficult, right? I mean, you look, this is the joint distribution, okay? So it's very difficult to say that is a Gaussian wizard, for example, okay? Now, we know, because of this, of the form of the prior, that if you take this expression and you take that lambda is given, right? If you fix lambda, you can write, so if you keep only basically the terms that depend on mu with fixed lambda in this expression, you basically get a Gaussian in mu. All right, you can see it if you close the square, and that's the Gaussian. All right, so from this, again, if you fix lambda, you get a Gaussian. And now how do you get then the posterior of lambda? Well, it's easy. You remember that the joint posterior is the conditional posterior times the variation distribution of lambda. So if you take logs of that, you can actually compute the, I keep going backwards. If you take logs of that, you can actually compute the approximation of the posterior of lambda. So if you do all the algebra, you get many different weird terms, okay? And if you have patience and you don't give up, you actually, all the formulas disappear, all the things cancel out, and you get a wonderful approximation for the log of the Q of lambda K that looks like that, okay? Where this WK inverse comes to be this, what you may think it's a complicated expression, okay? And nu K comes to be nu 0 plus NK. And you know what type of, this is the log of what distribution you think? So when you look at this, right, you can see it's a distribution of lambda K, but what type of distribution is this? So if I take the exponential of that, what do you think I get? So what you get is a wizard distribution, and here is the answer, okay? All right, so the combined basically distribution for mu and lambda is a Gaussian wizard, okay? So the Gaussian, the precision lambda comes with a wizard next to it, and here are all the parameters. So effectively, the approximation to the posterior of mu k and lambda k, it is the same form as the priors that we use for mu and lambda. The only difference is the parameters beta 0, and mu 0, etc. All nu 0, w 0 have been updated now, and these are sort of the updates of the parameters. So basically, using conjugate priors gave us even a variation approximation that is the same identical form. All right, so this is very nice. Okay, all right, so we don't keep going backwards again. All right, so then what you need to do to finish the conversation here, you need to go back to that equation with the responsibilities, and I'm going to put all of these things up So to see that there's a lot of heavy-duty algebra. So you remember the log of these responsibilities. These are the normalized responsibilities. Requires the expectation of the log of pi k. Requires the expectation of the log of this matrices lambda k. And the expectation with respect to mu and lambda of this. Okay? So you know what? You need to have currents to do this algebra. So here, let's complete this. You need the expectation with respect to mu and lambda. Notice what I have done here. I have done one trick, which is fundamental basically to every time you see this form and you have an expectation. I have written this as the trace of lambda times x transpose. Have you seen that before? It's a fundamental trick basically everywhere. When you get this, you write it. When you have x transpose lambda times x, you write this as the trace of lambda x transpose, okay? And then we need expectation with the posterior of mu lambda. We use the variational approximation of those. So we're going to do first an integration in k, then an integration in lambda. Really, the only thing you need is you need to know the mean of the wizard distribution to do that. So this time, basically, if you use the properties of the wizard distribution, are no problem. And it remains we need to calculate this expectation of the log of pi k, all right? Okay, so all right, so you can, I am not going to elaborate on this, okay? For those who, if you study on Wikipedia, the Dirichlet distribution, this expectation of a log of pi k comes to be basically a bi-gamma function computed on alpha k minus the sum of the alpha k's. This is the bi-gamma function. And then we have to compute this painful term that you will never see it anywhere in any machine learning book actually. Well, nobody has these calculations explicitly, but you will never see a discussion on how you compute the expectation with respect to a wizard distribution of the log of the determinant of a wizard distribution. All right? Okay? So, so there is a weird thing, okay? And I am not going to, am I going backwards? Yeah, no. Okay? So, so this is what we need. We need to calculate the expectation of this log of the determinant, right, that comes from the Gaussian, with respect to this, the variation distribution of lambda, which is a wizard, okay? And I remember when I first looked on this, a few years ago, I just couldn't find anything, and then accidentally, the miracles of Google, okay, I came across a reference that basically you can approximate this as a sum of DT squared distributions, and with some trivial algebra actually, which is on this slide that I'm not going to elaborate, you can actually compute analytically the expectation of the log of the determinant of lambda, and this is the expression where again this is the bi-gamma distribution. Obviously here my parenthesis should be inside the argument there, so I miss it. So bottom line, everything on this, okay, can be calculated, and I'm going to give you a very compact form, and the very compact form is what you see on the bottom, okay? So this involves this curly pi, which we define it here to be the exponential of this expectation, this curly lambda that we define to be the exponential of this expectation, and then this term inside, where nu k is nu 0 plus nk. All right, we showed this earlier. So basically, if I can find a slide that is a summary of everything, this is the whole algorithm. I mean, if somebody gives it to you, right, you can program it in a few minutes, okay? But of course, you have to derive it, right? If somebody gives you, will you actually trust any of these results? I will not, okay? Now, you notice the algorithm is written as an E step, M step because of the similarities with the expectation maximization algorithm. So in the each step, you have to calculate basically the responsibilities, and to calculate the responsibilities you need these expectations, this curly pi k and the curly lambda k, and this is the formula for these responsibilities. Once we have the responsibilities, we can go in the m step, calculate the effective number of points on each Gaussian k, the effective mean values and variance, and update all the parameters, and then you keep iterating, and you will converge. Okay, you will converge. And again, as I mentioned, these calculations have been extended to an infinite mixture of Gaussian processes, and very recently have been extended also to an infinite of Gaussian distributions, and also an infinite mixture of Gaussian processes. Okay, so I'm going to do one example. There is a Python code, okay? I'm going to post the slides. Actually, on these slides, some of the equations that I'm not going to show you today, somehow they don't show very well because they were typed on a Mac. So I need to sort of retype some of the equations. But we will fix it today, so hopefully. So here is an example that has a mixture of 6 Gaussians. So these are my data points. And the ellipses that you will see is basically one standard deviation density contours. Each of the points, I trust, that has a red ink, all right, that inside each ellipse that corresponds to the mean value of the mixing coefficient. And this is when you start, all right, so these are the prior mixing coefficients, but as we will continue this will be, the color will be based on the posterior responsibilities. So this is how you start, okay? This is iteration 15, okay? All those are the different Gaussians, basically, that you compute. This is iteration 60, and this is iteration 120, so basically the model collapsed on 2 Gaussians. Now, you may say, what happened? You say, I have a mixture and collapse on 2 Gaussians. Well, yeah, because these priors that we have used for, they enforce, what's the buzzword? Sparsity, okay? So these priors we use basically kill some of the components, okay? And obviously, that's why you use the same ideas, right, for an infinite mixture. You're not going to have an infinite mixture. So if you say, start with 500, you will only hope that 500 will drop down to 510, So here it drops down to 120 without you having to do. So this sparsity is done sort of not in a sort of violent way, say, use 2 components. Smoothly, the other 2 components are not coming because the responsibilities taken for the data points are basically 0. All right, so if they're 0, they're not plotted. Okay, this is basically another the same problem, sort of different data sets, and again, all right. Strongly, I always advise you to look at this code. Actually, if you look at this code, right, only to see these equations of the algorithm stated there and how they're updated, you immediately say, I understand how this thing works, okay? So here in this case, 6 components survive, all right? And it takes lots of iterations, 90 iterations. You notice this is the lower bound, and you notice it monotonically increases, okay? And this is this, what do we plot here? So these are, these different, basically, I suppose, these are the posterior values of alpha k, so, okay? The posterior values of alpha k, and you notice eventually, after iteration 94, so this is some intermediate, I suppose, iteration, after iteration 94, only 2 of the component k's survive, Okay, so this actually may be the same data set as the one I showed you with the Python code just a few seconds ago. All right. Don't want to say anything on that. Okay. Let me see what else. I know what I need to tell you. So we need. You may ask me, since you got very excited with this, you may say, and where's the variational? Where's the lower bound? Right? Where's the predictive distribution? Is there any hope to actually compute any of that? So let me. I'm going to jump on slide 47. Because obviously, what's the point of training a model, right, and saying here is how the data fit, in so many components? What I'm interested to know is, can I actually compute the posterior of a new data point? Okay? So look at this equation. So this is the predictive posterior distribution. Tell me exactly everything you see on this equation. I see triple integrals and summation on z, so tell me exactly what's going on there. How do you calculate the predictive distribution? What do I supposed to have here and what do I supposed to have there? What's the predictive distribution? Would be the likelihood if I knew all the unknown parameters and latent variables. So these are the parameters, right? And this z hat is the latent variable corresponding to x hat. In other words, if I knew what component, what Gaussian component in the mixture generates the point x hat, all right, this would be the likelihood. Of course, I don't know that, all right? That's why there must be an integration on all the unknowns, including z bar, and I put as a summation because z bar takes what values? It's a binary variable, right? So I'm going. It's a discrete variable, so I'm going to integrate on z, and then of course I'm going to have there is so there is a distribution on z given pi. There is the posterior of pi mu lambda given x, all right? And here you notice pi mu and lambda have to integrate them out because they're continuous variables, okay? So, all right. What I'm doing this is I am taking the summation explicitly over the number of components, okay? And so I'm substituting those two terms with pi k times n of x bar generated by this Gaussian that you see here. You understand how this comes, right? If I sum, if I look at this term, knowing that I am on the Gaussian k, this term will become the mixture component pi k, the mixture coefficient pi k, and this will become this Gaussian. And the rest is basically the posterior pi mu and lambda given the data. And obviously, this posterior is very complicated, so we're going to approximate it with a variational distribution, so q pi, q of mu k, lambda k. So this, what distribution we got on this? You remember we got, this was factorizing over data in k, and this came to be factorization of the k of Gaussian wizard distributions, okay? And of course, good luck now trying to perform this integration, all right? Now, good luck means you never give up, right? Because if there is a closed form solution and you go and you say, no, I wrote a nice computer program to do this, people would be laughing. It's like, you must be kidding, Go and read the books first, because there is an analytical solution to this. Can you guess, before I show you anything, can you guess, just from your gut sense here, what type of distribution this may come to be? Just guess. So here we have a Gaussian mixture, that's how it trained, right? It became components. And I would try to predict for new x, what's the probability? What do you think is going to happen? Just give me some choices. What may come? So the model is, again, it collapses to some mixture of some capital K components. So what will the predictive distribution look like at the end of the day? I mean, what will not surprise you in other ways? Will it be surprising to you if it comes to the mixture of Gaussians? Mixture of Gaussians? No, I mean, it will not surprise me. And actually, it doesn't come to be a mixture of Gaussians unless you have a lot of data. But it comes to be a mixture of what distributions? What is very close to Gaussian? Student T distribution. Okay? So it comes to be a mixture of student T distributions, and only on the limit of when you have a lot of data, so the prior effects basically disappear, the student T mixture becomes a Gaussian mixture. And, okay? So, the algebra is actually is not as painful as I make it look like, right? So you will you will need basically the expectations of these coefficients pi k coming from the Dirichlet distribution. You will need basically to work with this, okay? And so you can see here actually so if you plug in everything we know, it comes that the predictive distribution is an integration of the lambda, for each k, lambda k, of a Gaussian, okay, but with a precision that you see here, that's a wizard distribution. Okay? So again, it is an integration of a lambda of Gaussians with wizards. You know actually what this is? And actually I should have given you this as a homework, right, in an ideal environment, because somewhere even in Bishop's book, it has a trivial example that tells you, when he introduces, if I remember early on, like chapter 2, he introduces this student T distribution. You know how he introduces it? As a mixture of Gaussians, where the precision in the mixture, so the components in the mixture are what? They are gamma distributions. So actually, obviously you can see here, if you have a multivariate Gaussian, right, and you take for this precisions a wizard, you know you will get a student T distribution, a multivariate student T distribution. Okay? If you don't believe me, look on chapter 2, where he introduces a student T, with sort of this construct, but in one dimension. Okay? So basically here, what we have is exactly the same thing. So to figure out that it's a student T, it's some trivial algebra, basically looking on how student T distribution looks like, and this is what you get. Okay? All right? Okay? So alpha k, you remember alpha k comes from the Dirichlet posterior on pi that we got, right, are the coefficients in the Dirichlet distribution. Alpha is the sum of alpha k, so these are the mixed components. And then inside you have the student T with a precision basically that is given by this formula, and the WKs we had computed them before from this Gaussian wizard distribution. Okay, so very nice formula. Okay, all right. I don't know why. So maybe I should have put. Okay, so it's an approximation, obviously, of the predictive distribution. It's an approximation because the posterior of the parameters we used was not the exact posterior. It was the variation approximation. Okay. So there is an exercise in the notes, and I think that part I already corrected. So if you are interested, what you can do is, and again, it's a very nice exercise. If you look at this formula and say, let me look at all the parameters, what happens when I have a lot of data. So when you take n to go to infinity, right, when you have a lot of data, you can see with some trivial calculations, basically, that this predictive posterior distribution comes to be a mixture of Gaussians. Okay, and you could actually even have guessed this answer, all right? Because if you have lots of data, forget all the priors, forget everything. You know what? Then you think. So every Gaussian is defined by the average of the points, right? When we train it, that belongs to every Gaussian with this covariance. Okay, and then basically the mixing coefficients is, well, how many points are on that component versus the total number of points. Okay, I mean, you could have, if you're desperate, right? Somebody tells you predict. That's an obvious answer. No algebra is needed. But obviously, if you try to do all the algebra and then you get some weird answer, and when you have lots of data, you don't bother to say, is this correct? In other words, is it going to give you this? If it is not going to give you that, something is very wrong with the algebra. Okay? So in this case, when you take the limit to lots of data, the algebra comes to be correct. To do this limit, you have, and I encourage you to try it. I mean, everything's in the notes. At least follow it and don't get dizzy. Okay? So if you follow the algebra, you have to use nice approximations. I can see, because there's gamma functions, you have to use Stirling's approximation formula and approximation for entropies. It comes out basically all the posterior distribution, because you are the limit of many data become delta functions, and at the end of the day, with delta functions, you get the right answer. Okay. All right. I don't really have 3 minutes, so what did I tell you we need to do? We need to go back. What slide was it? 16, thank you. Just to tell you how you can generalize this, and okay. Okay. All right. So, really, because, we talked a lot about Gaussians, right, and the likes, you can actually generalize this for many, many problems for situations where the joint likelihood of x and z, all right, comes from the exponential family. Okay? And that includes many distributions. So what I do here is I expand the joint likelihood, all right, in the form of an exponential family distribution. So these are the sufficient statistics. These are the natural parameters. This is a normalization factor. This is a function of x and z, all right? So, so actually in the notes, okay, that I'm going to give you, you can use sort of this little derivation that I have on the next slide to actually rederive all the calculations we did for the multivariate Gaussian, all right? Because this is a very general formalism, okay? So if the joint likelihood looks like that, for the hyperparameter theta, you put a prior that is also from the exponential family. So you copy the information from there, all right? So your sufficient statistics here really become mu 0 x 0, okay? This mu 0 becomes your coefficient that defines this prior, and f of x 0 mu 0, okay? So you can read Bishop's book or look at my notes in the fall for more information on the exponential family. But basically, you can put on this form many distributions, right? So the question is, can we actually derive variational inference approximations for this general scenario? If we can, then we have solved about 50 problems all in one slide. And the answer, yes, you can. So what you have to do, let me put everything up because the time is over. Okay. Okay, so basically you have to use exactly the same ideas as before, all right? So you factorize this as q of z times q of theta, and you are looking for q of z and q of theta to be the exponential family, and surprise, surprise, q of zeta, the octuple, comes to be exactly in the exponential family. The only thing you need is the expectation of the parameters, and Q theta comes also to be in the exponential family, and you can see the updates are standard, and the only thing you need is the expectation with respect to Z of the sufficient statistics U of Xn and Zn. Okay? So basically, every problem where this distribution is the exponential family can fit in within this variation approximation in a sort of an E-step where you compute this expectation using Q of Zn, and then you plug this in here and you compute this variation distribution. Actually, the only thing you need is you need the expectation of theta, so you iterate and you can get, tight, you can get the results for multivariate Gaussian, you can get the results, any distribution, any example that you see in the literature, you can use these formulas and it will fit in. All right, so I'm going to leave you there, and we're going to be back on Tuesday. Enjoy Friday, happy Easter, and see you on Tuesday. I like it.